In this lecture, we'll look more at JavaScript prototypes, and we'll redesign our linked list class from earlier topics to make use of linked list.prototype. Take a look at the linked list class in the slide. This is a derivative of the linked list2.js file from lecture, from an earlier lecture. And as you can see, I've modified the add and the drop functions from what they were before. Both now return an integer indicating how many items were added, which is trivially 1, or were dropped, which is not so trivial. It could be anywhere from 0 to every one in the list if all of them match the val parameter up here. And the drop is no longer recursive. I didn't want a distracting concept in there, and it's also hard to make the recursion count the number of dropped objects. So the new non-recursive drop keeps traversing even after dropping a node. And the code for drop is in the loop instead, as you can see. It looks for more nodes to drop and counts the number that it finds and drops. Now, per usual, this is about JavaScript more than linked list logic, but also per usual, I still want you to understand the code. So, read this carefully, this new drop, and answer the question, why do I only advance prior on line 27 instead of on each and every loop iteration? Doesn't it have to follow temp? You may find it helpful to go back and review the way this code was in the very first linked list revision as well. So, coming back from a pause, prior has to remain one node behind temp, yes, but it isn't necessary to change it when we delete the node at temp and move temp to the next node, since the node between prior and temp has been dropped. So prior is still one node behind temp in that case. Now, with those details aside, let's look at the main change to linked list. Every function is in linked list.prototype now, instead of directly in the linked list objects as it was in earlier examples. Per our recent discussion on prototypes, this should cause no difference in the behavior of the linked list objects. All the functions will work fine. And note, it's also more space efficient to do this. Without the prototype, each linked list object has to have its own copies of the references to the functions, though not separate copies of the functions themselves. There's always just one each of those. With the prototype, each linked list object needs only its proto property, plus any object-specific data like head. And of course, we can adjust the function properties of all linked list objects together by tweaking the prototype. So it has several advantages. Such design is standard practice in professional JavaScript, and from now on, your methods should go in the prototype unless there's a compelling reason to do otherwise. Now, we've also upgraded the test driver for linked list. Let's take a look at that down here. As you can see in the diagram, it's a separate file and loads linked list .3, I should say, .js, the file we were just reviewing. Now, we'll discuss this count linked list on line 2 in a moment, but note for now that the add and drop commands in the command interpreter here report the number of nodes that were added or dropped. And note the addition of a count command as well, even though there was no node counting function in linked list. And so we come to count linked list. This is a version of linked list that counts its nodes and reports the count via a function getCount, which you can see is called in the test driver on line 16, at least in some cases. Now, count linked list works by deriving from linked list JS style. On line 8 of the test driver, we have a construction of a new count linked list, and this implies a constructor call, so let's start there. In file countLinkedList.js, and see how you do inheritance in a language that has no traditional classes, just prototypes and constructors. Lines 1 through 4 are the countLinkedList constructor. It doesn't do much. Like any good derived class constructor, it defers all the base class initialization to the base class constructor. The only initialization it does itself is of a new property count on line 3, which will be specific to count linked list objects. Now, line 2 requires careful explanation. Remember, we're in a call of new count linked list. That means an empty object was created and passed to us as our context object, which we're referring to by this. We want to run the linked list constructor function on it to do linked list related setup, like setting head to null, for instance. So here's question 1. Why not just use this dot linked list? Wouldn't that make our context object be the context object for the call of linked list? Stop and think about that. And coming back from a pause, it would actually if it were allowed. But linked list is not a property of this, and the statement is rejected for that reason. You can't refer to this dot linked list if it's not a property of this. Flexibility in choosing this, the context object, is important in much of JavaScript design. The same typeless freedom that lets a parameter or a variable be of any type also allows this to be of any type. Specifically, this does not have to point to an object that has the function in question as a property, or has a prototype that does. The only requirement is that this have all the properties needed by the method. If it comes from a completely different constructor, that's fine. But you can't just pick a this via the syntax whatever I like dot whatever function. That syntax does require that whatever function be a property of whatever I like, or of its prototype. Instead, you use the apply function, which is a property of every function object, including linked list. The apply function calls back the function that it was called on. That would be its context object, right? Linked list in our example. For this callback, apply applies first parameter, this in our example, as the context object. And if there's a second parameter, it passes as actual parameters the elements in that second parameter, which second parameter must be an array. If the second parameter is missing, as in our case, then no actual parameters are passed, only the this parameter. So line 2 does what we were trying to do with this dot linked list. It calls linked list with our this as the context object. Got all that? Think it through carefully, because almost all serious JavaScript code makes use of apply. And we have an in-lecture question on it coming up next, a couple of them in fact. So the in-lecture question is, please translate this conventional function call, and I will drop it into the slide, although it's, as always, in the notes, and translate it into an apply call. You'll need to properly pass to apply the context object and the array of actual parameters. Thinking about that for a bit, possibly quite a bit. Fairly tough question. The answer is that we will write s1.subster.apply. We're going to do an apply to call the subster function, and we do still need the s1.subster just to get to the function. But the apply call will take the place of the conventional function call. Its this parameter will need to be s1. And the actual parameters, as we said, need to go into an array, thus, so that will replace the call above and do the same thing. Now, actually, I just lied when I said you needed to still say s1.subster to get to the function. That's one way, but you can get to subster and call it without that. So rephrase the answer I just gave here, using s1 only as a parameter to apply and not otherwise. Remember, s1 is a capital S string. That should help. Again, coming back from a pause there, we could do string.prototype.s1 dot subster, and pass it s1 and bracket comma 4 as before. Thus, remember that almost all function properties are actually in the prototype, which is accessible via the constructor. Okay, so after that long but important digression, we can see that line 2 calls linked list, the constructor, on our count linked list object. Okay, but what value for proto and constructor does our new list object get if it receives the attention of two different constructors, whichever one was invoked by new, which of course is count linked list in our case? We say the constructor sets those two properties, but in truth the constructor is a function like any other. It wasn't declared with some constructor label or keyword, aside from the style convention of a capitalized name, and it doesn't know that it's being called via new. It's really the new operator that sets up those two special properties. So, in summary, after the new count linked list call, we have an object with count linked list prototype and constructor property, but whose data has been partially initialized by linked list. Now, what about its function properties? These come from count linked list.prototype, of course, but here again we extend linked list.prototype and reuse linked list's prototype as much as possible. Starting with line 6 here, we can see that it sets up linked list.prototype as the proto property of count linked list.prototype. In other words, it's count linked list.prototype's prototype. Remember that prototypes are themselves arranged in a chain ending with object.prototype, and we're extending that chain here. This means that any functions omitted from count linked list.prototype will automatically default to linked list's version. This is as it should be for a derived class. Now, given this, what happens if I call apply? And importantly here, I mean the apply for our linked list, not the function.apply, which is different. So what happens if I call apply on a count linked list? Note that apply is not in the prototype for count linked list. Coming back from a pause, it will call the linked list version, since if it's not found in one prototype, JS will look at the next prototype in the chain. So any functions omitted from count linked list.prototype will automatically default to linked list's version. And that's just as it should be for a derived class. If you don't redefine the base class methods with derived ones, then you get the base class versions. Now let's look at two of the functions, add and drop, that are supplied in count linked list.prototype, here and here. These rely on their linked list versions, again, to do much of the work. As you can see, they call the add for linked list and the drop via apply, saving the result in dropped or added, and then they do their own value added work of incrementing or decrementing the count, and then ultimately they return in turn the number that were added or dropped. Now in Java, those first two lines, or those two first lines I should say, would be super parentheses calls. And in C++ they'd be linked list :add or linked list :drop calls. It's quite common for a derived method to call the base method to do most of the work and then add a little bit of embellishment of its own. And that's how you do this in JavaScript. And in lecture question, why couldn't these calls just be this.add of val or this.drop of val down in the drop function here and here? The context object is a count linked list, which has the necessary properties to work with the linked list add and drop functions. Coming back from a pause. Well, because this.add, if that's what you wrote here, would follow the proto property of this, which is a count linked list, right? And thus would arrive back at the count linked list.prototype.add function, which in fact is the one we're in the middle of. It would be an endless recursion. You can see why having a clear visual picture of all these prototypes and references is essential to debugging JavaScript. Use the diagram I drew in an earlier lecture, perhaps reorganizing it to your liking, and think it through carefully until you can keep track of all this. And, by the way, finishing up the prototype, there is one entirely new function, getCount, which we've added to the countLinkedList.prototype to return the new count property. Finally, let's look back at the driver's implementation of the count command on lines 18 through 19, on lines 15 through 16, to see that it checks to see if the list in question was constructed by countLinkedList. Right here. It calls getCount if so, or prints NA if not. And this constructor test is the analog of a list instance of countLinkedList expression in Java. You have the two source files, by the way. I'd recommend trying out the program to see that it all does function as we said, and try printing out the counts and that sort of thing. And one more topic here before we wrap up. I'm going to quote from earlier in this lecture. You use the apply function, which is a property of every function object, such as linked list. Now, that's a lie. Why? If apply is not a property of the function object, what is it a property of, and why can we write linkedList.apply? Coming back from a pause, the answer should be a bit of a reflex by now. Apply is a property of linked list's prototype, not of linked list. What, now constructors have proto-properties too? Of course they do. It's hard to view a function as an object since it looks so code-like, but never forget that it is simply a normal object with a special added code property, plus that mysterious closure context that we have yet to discuss. So, what's the constructor for functions? Well, predictably it is function, with a capital F. And one may actually create a function object via this constructor. Indeed, you can frame up some JavaScript code in a string as the program runs and create a new function that didn't exist when the program started by passing that code you made to new function on the fly. This is beyond the scope of this course, but you can bet we'll do it in the more advanced JavaScript course. For now, it's enough to know that function is the constructor of every JS function, and that the functions have proto-properties that contain a bunch of functions like apply that deal with function objects. And note I have carefully described this as linked list's proto-property, trying to avoid calling it linked list's prototype, even though it is, because this would introduce confusion between linked list.proto and linked list.prototype, which is not the same thing. Recall I said earlier that the property prototype was poorly named and should have been called model property. Linked list.prototype is the prototype for objects constructed by linked list. It has function properties like add and drop. Linked list.proto is the prototype for function objects containing function properties like apply. And then, final question, fill in this equality check so that it is always true, assuming f is some function, and without using f in the blank. And coming back from a pause there, it's the prototype of f, the proto of f, and that would of course be the same as function.prototype. It gets its prototype from its constructor's prototype property, like any other object.